The Unit 2 paper. All right, so let's get started. Module 1. It says, a curve is defined parametrically as x is equal to t over 1 plus t, and y is given by t cubed over 1 plus t. Determine the gradient at the point a half, a half. To determine the gradient at this point, we are going to need to find dy by dx. So let's go ahead and find dy by dx. So first, to find dy by dx, we know that dy by dx is dy by dt times dt dx. So let's find dy by dt. dy by dt is, we can use quotient rule to find dy by dt. So dy by dt is start with the bottom, then we multiply it by the differential of the top, and the differential of the top is 3t squared minus the top, which is t, times the differential of the bottom, which is 1 plus t, over the bottom square. So we start with the bottom, differentiate the top, 3t squared minus the top, and the top is t cubed, minus the top. Start with the bottom times the differential of the top minus the top times the differential of the bottom. The differential of 1 plus t is just 1. So it's just minus t cubed over the bottom square, which is 1 plus t all square. We can go ahead and simplify this to be that dy by dt is, if you're to expand this, you get 3t squared plus 3t cubed. 3t cubed minus t cubed is 2t cubed. And then you have this one times 3t squared, so it's 2t cubed plus 3t squared. Over 1 plus t all square. So that's dy by dt. So now let's go ahead and find dx dt. So dx dt, that means we're differentiating the function now. We're differentiating x with respect to t. We start with the bottom, which is 1 plus t, multiplied by the differential of the top. The differential of the top is 1, minus the top, which is t, times the differential of the bottom. The bottom is just differentiate 1 plus t, just get 1 over the bottom square. And so if you work out 1 plus t minus t, 1 plus t minus t, the t minus t cancel, so you just get 1 over 1 plus t all square. So now we may proceed to go ahead and find dy by dx. So dy by dx, as we know, dy by dx is equal to dy by dt times dt dx. So it's going to be equal to this, which is 2t cubed plus 3t squared over 1 plus t all square and that is being multiplied by dt dx. Dt dx is going to be 1 plus t squared over 1. After we do that now, we're going to observe that 1 plus t squared cancels to 1 plus t squared. And so dy by dx is just this. Now we need to find the value of t when x is a half and y is a half, so that we can plug in that value for t. So let's go ahead and find that when x is a half, we get that t over 1 plus t is equal to half. So we need to find what t is. So we cross multiply and we get 1 plus t. 1 plus t is equal to 1 plus t, not 1 plus 2t. 1 plus t is equal to 2 times t is 2t. And so we bring over this t here. And so we're going to get t equal 1. T equal 1. Let's check it. 1 over 1 plus 1 is a half. Yeah, so t equal 1. So t equal 1. And so now we're able to find dy by dx at a half. So dy by dx is going to be equal to, or we can rather say, the gradient at that point. All right. So the gradient at the point a half. So the gradient at the point half is equal to, plug in when t equal 1, you get 2 times 1 cubed, which is 2 times 1, plus 3 times 1 square, which is plus 3 times 1. And so the gradient at this point is equal to 5. Nice and easy. That's the first part of this question. The gradient is 5. Continuing right along. It says, hence, determine the x and y intercepts of the tangent that touches the curve at the point a half. Determine the x and y intercepts. So first we're going to find the equation of the tangent. The equation of the tangent is going to be given by y minus yp. So it's y minus a half is equal to the gradient of the tangent, which we find is 5 into x minus a half. All right, so let me see. This is the equation of the tangent. This is the equation of the tangent, so I'm going to rewrite this now as y is equal to 5x. Then I have the 5 times minus a half is minus 5 over 2. And I add a half to minus 5 over 2, so 0.5 plus minus 5 over 2. And I get minus 2. So this is the equation of the tangent. The equation of the tangent is 5x minus 2. That's the equation of the tangent. Now let's look what the question said now. It said, hence determine the x and y intercepts of the tangent that touches the curve at the point a half. Determine the x and y intercepts of the tangent that touches the curve. So when it's talking about x and y intercepts, So I don't know how this curve look. I'm just going to draw some random curve. So we have some random curve. Let's say the curve looks something like this. And we have some tangent looking something like this. And what did they say they want? They say they want to determine the x and y intercepts of the tangent that touches the curve at x and y intercepts, meaning where it crosses the axis. So this is what they want. They want this here and this here. So they want the x and y axis intercepts. So now we know that the x-intercept, so the x-intercept occurs when y is 0. So if you were to set y to be 0, you get that x-intercept. Let's write it down. So the x-intercept occurs when y equals 0. When y is equal to 0, what you're going to get is 0 is equal to 5x minus 2. And so you get that x is 2 over 5. And so the x-intercept is the point 2 over 5, comma, 0. That's the x-intercept. For the y-intercept occurs when x is 0. So the y-intercept point is going to be when x is 0, y is negative 2. So 0 minus 2. And that's that. All right. I know my sketch is really off because a half would have been over here, but I'm just drawing something to see what was going on. All right. So the x-intercept, the y-intercept. Nice. Moving right along. It says let f of x be, let's go back. Let f of x be sine kx times sine aky. Determine dou 2f of xy of dou x by dou y. So we need to determine dou 2f of xy of dou x by dou y. To determine this right here now, that means we're going to differentiate with respect to y first, and then we're going to differentiate with respect to x. So let's go ahead and do that. We need to differentiate with respect to y first, and then differentiate with respect to x. Differentiating with respect to y first, we keep this first part as a constant. And so I'm not going to write all of this. I'm going to write fy. Fy really means dou f by dou y. So finding fy first, differentiating with respect to y. So this is a constant. So I'm going to get, oh, I don't need to do that. So the sine kx is a constant. So I just put back my sine kx multiplied by, now I can differentiate sine aky. When I differentiate sine aky, I get cos aky times the derivative of aky, and the derivative of aky, I could put it here, is a times k. All right, so that would be fy. Now next we need is dou 2f of dou x dou y. So we need to find now, differentiate it with respect to x now. So it's fyx. So fyx now. We need to differentiate fy now with respect to x. So we're going to differentiate this with respect to x now. Differentiating this with respect to x now, we're going to keep this part, a cos aky, as a constant. So differentiating this part with respect to x, I'm going to rewrite it as ak cos aky, just to show that that's a constant. Then when I differentiate sine kx, I get cos kx. Then I multiply it by k. So the final answer is equal to ak squared So the final answer is A times K squared cos AKY times cos KX. Nice and easy. So that takes care of this question. Nice. All right. Now this question says use the Moivre's theorem to show that sine 5 theta is equal to sine to the 5th theta minus 10 sine cube theta times cos squared theta plus 5 cos to the 4th theta sine theta. To use the Moivre's theorem and do this, all we're going to show is, well, the Moivre theorem tells us that cos theta plus I sine theta so the Moivre's theorem tells us that cos theta plus I sine theta let's write that down. The Moivre's theorem tells us that the cosine of theta plus I sine theta, when all of this is raised to the nth power, the Moivre's theorem tells us that it is equal to cos n theta plus I sine n theta. That's the Moivre's theorem. Cos n theta plus I sine n theta. So what does this mean? That means if we were to let n equal 5, if you let n equal 5, look what's going to happen. If you let n equal 5, you're going to get cos theta plus I sine theta to the n, which is now to the 5th power. You got cos theta plus I sine theta cos theta plus I sine theta raised to the n is to the 5th power, and this is equal to cos n theta, which is cosine 5 theta plus I sine 5 theta. Now all we need to do is expand this left hand side, and we would have learned Pascal triangle, its first term to the 5th. So this is going to work out to be cos to the 5 of theta. So you have to remember Pascal triangle, it is 1, 5, 10, 10, 5, 1. So it's cos to the 5th plus 5 cos to the 4, 5 cos to the 4 theta times I sine theta. Then you go 10 and it's going to be plus 10 cos cube plus 10 cos cube theta times I sine theta square plus 10 again, but now it is 10 cos square theta times I sine theta cube hope we're following the pattern. It is 1, 5, 10, 10, then equal 5 again. And notice that we're decreasing in powers in cos and increasing in powers in I sine theta. So now it is plus 5 cos theta plus 5 cos theta times I sine theta to the 4 plus 5 cos theta plus I sine theta to the 5th. And that's how we expand all of that. Plus I sine theta to the 5th power. Nice. So finally we finish expand out all of this. Then what do we do next? What we do is now we're going to equate it to the right hand side, and the right hand side, which was just cos 5 theta cos 5 theta plus I sine 5 theta. Now when we equate it to the right hand side now, all you need to do is they want sine 5 theta. So that means that you're going to equate your imaginary parts. Equating your imaginary parts, you're going to go through and say, this is going to give me an imaginary number. Sine square is -1, so that's a real. This is going to give me an imaginary number. And this will give me an imaginary number. All right? So now that means that this now expanding the left-hand side with just the imaginary part. So we're equating imaginary parts now. All right. Equating imaginary part. Equating the imaginary part. What we're getting is 5 cos to the 4 I sine theta. Five cosine to the 4 I sine theta. I'm going to put the I on the outside here. So I times 5 cos to the 4 sine theta. For this part now, I'm getting I cube sine cube, but I cube is minus I, so I'm going to write it as minus I times 10 cos square times 10 cos square theta sine cube theta and then right here I have sine I to the 5th. I to the 5th is just I. So then I just have I sine to the 5th and that's equal to I sine 5 theta. Nice. So to finish off this question now, we're almost complete. All right, so to finish off this question, all we have to do now is everything in the answer is in terms of sine to the 5th minus 10 sine cube plus 5 to the 4 cos theta sine theta. So we're done. All we need to do now is divide through by I, and dividing through by I, so we're going to put this part on the left part first. Dividing through by I, as you can see now, so when you divide through by I, you get sine 5 theta is equal to, when you divide through by I, this part becomes sine to the 5th theta, sine to the 5th theta, minus, well, plus, when you divide through by I, you get plus 5 cos to the 4th theta sine theta then you put now minus, divide through by I, you get minus 10 cos square sine cube. So minus 10 cos square sine cube theta. And that's your right hand side. That proves it. Soft. So we finish. That proves it. There it is. Minus 10 sine cube cos square. 10 sine cube cos square is the same as 10 cos square sine cube. 5 cos to the 4 sine theta. 5 cos to the 4 sine theta. Sine to the 5th. So we're showing it. Just put it in different order. So you write shown. And soft with a capital T. Soft. Nice. All right. Now let's look at part D. Part D says write the complex number z in the exponential form. So in order to write this complex number z in exponential form, you first need to identify that z equal 1 minus I. That's in the second quadrant, because 1 is over here, minus, so this is 1. This is, let's say 1 is here, then minus, oh, it's in the fourth quadrant, my apologies. It's in the fourth quadrant. All right, it's in the fourth quadrant. So it's in the fourth quadrant. So we can find theta now. And so theta is just going to be equal to tan inverse of y over x. And so theta is equal to tan inverse of minus 1 over 1. That gives you, I think that's minus pi by 4. So that's the angle in the fourth quadrant. Then we need to find r. R is going to be equal to 1 square plus minus 1 square, all square rooted. And that's equal to the square root of 2. It's equal to the square root of 2. That is r. So now that we get this for r, we're good. So therefore we can write that z is equal to the square root of 2 e to the I times theta. So we're going to write it as square root of 2 times e to the theta, which is minus pi by 4 times I. That is z in this case. Nice. Moving right along, it now says, hence, show that 1 minus I to the 9 is 16 times 1 minus I. Okay. So, this is what we want. Hence, show that. Now remember, we just showed that z, which is equal to root 2 e to the minus pi by 4I. This is z, root 2 e to the minus pi by 4I, where we said that where z is 1 minus I. This is z is 1 minus I. All right, so all we need to do is go ahead and continue. So we need to just go ahead now and continue and raise this to the 9th power now. So z raised to the 9th power is going to be the root of 2 raised to the 9th power. Let me try to fix this. So z is just now the root of 2 raised to the 9th power. We're just raising it to the 9th power times e to the 9 times this now is e to the minus 9 pi by 4. Nice and easy. Now you may proceed and How I like to do it, I like to then put it, I like to go from exponential to polar form. So in polar form, what this is saying is, in polar form, this is the root of 2 to the 9th power, and it is being multiplied by the cosine of minus -9 pi over 4, cosine of 9 pi over 4, plus I sine minus 9 over 4, minus 9 pi over 4. Nice and easy. So that's z to the 9 in this case, where z to the 9 is this. So z to the 9, which is this, is pretty much now saying that 1 minus I to the 9th power is equal to, put this in a calculator, root of 2 to the 9th power. So root 2 raised to the 9th power, root 2 raised to the 9th power is 16 root 2. So root 2 to the 9th power is 16 root 2. And 16 root 2 is multiplied by, putting in a calculator, the cosine of 9 pi by 4. So 9 minus 9 pi by 4. The cos of that is root 2 over 2. In this case, it's root 2 over 2. You can write root 2 over 2 as 1 over root 2. This is really 1 over root 2. Plus I sine minus 9 pi by 4. So minus 9 pi divided by 4. And the sine of that is minus 1 over root 2. So it's minus 1 over root 2 times I, when you put those in a calculator. And finally, all you have to do now is expanding the root 2, and so you're going to get 16 times root 2 multiplied by 1 over root 2 is 1 minus root 2 times minus 1 over root 2 is minus I. So we finished. So we proved it. Nice. That takes care of question 1. No issues. Moving right along. We get to question number 2. Question number 2 has integration. So it says that we're supposed to evaluate the integral of x to the 5th times cos x cubed. Now, typically I like to call these integrals I. I like to call these integrals I. All right, I like to call it I. If I'm going to use a substitution u, I'm going to use a substitution first, u as x cubed, because I don't like to be integrating cos of like e to the x. You don't like to be integrating cos of these things. So anytime you say cos with a bracket, let's call the thing in the bracket u. Cos, so u is x cubed. So that gives us that du is equal to, when we differentiate 3x squared, we differentiate x cubed, we get 3x squared, my apologies. So du is 3x squared. After we get du being 3x squared, we're good. So now I is going to be equal to, and remember du is 3x squared dx. So I is now going to be equal to, now this x to the 5th, let me put it down right here, x to the 5th can be broken up as x cubed times x squared. I can always separate x to the fifth as x cubed times x squared. So I'm going to rewrite this integral now as the integral of, instead of saying x to the fifth, I'm going to write it as x squared times the cos of x cubed times x cubed dx. And let me change the position. Let me put the x cubed here and the x squared here. And you might say, sir, so why you do that? Why did you break up x to the fifth? I broke up x to the fifth because I need to generate 3x squared dx to be du. So I need a 3 right here. So if I put a 3 right here, I'm going to have to put a 1 over 3 out here. All right. And now I can substitute for u. So now I get that I is equal to 1 over 3 times the integral of x cubed is u, so that becomes u. Cos x cubed now becomes the cos of u. And then 3x squared dx becomes du. So now we're good. When you get to this part now, we're going to use integration by parts now. This looks like by parts now. So now we can use integration by parts to do this. So to do integration by parts, we usually use u and v. Since I already use u and v, let me write down the by parts formula. Just for those who don't remember again, using by parts formula, the integral of u dv is equal to uv minus the integral of v du. That's the by parts formula. So if we're going to apply this by parts formula, what we're going to get now is this I is going to become equal to, we're going to think of this now, think of this as a u and this as a dv. So it's going to become, right, equal down here, it's going to be equal to 1 over 3 times 1 over 3 times uv. What's uv? This is like your u and your v. If cos u is your dv, when you might not be following. I'm going to use a different letter for u and v in this case. I'm going to use f and df. So in this case, I'm calling fu and so df equal 1. And in this case, I'm calling ds. I'm using f and s. ds, I'm calling ds cos u. And in this case, I'm calling s. When I integrate cos s, cos u, when I integrate cos, I get sine. When I differentiate sine, I get cos. When I integrate cos, I get back sine. So it's going to be u dv in this case, which is f ds, is equal to uv, which in this case is going to be fs, f times s. So it is u sine u. So it's 1 over 3 u sine u minus the integral of, this is now v du. In this case, it is now s df, which is now the integral of sine u. With sine u du. And I close up that bracket. So now I can proceed. So finally, the answer I'm getting is 1 over 3 u. But remember, we said that u was x cubed. So it's 1 over 3 x cubed sine x cubed Since I expand in the 1 over 3, it's going to become minus 1 over 3. Then the integral of sine u is minus cos, so it becomes plus 1 over 3 cos u. But remember, u is x cubed, so it's plus 1 over 3 cos x cubed plus some constant of integration. I can call that k. So that's how we do that question. Nice. Wasn't too bad. 1 over 3 x cubed sine x cubed plus 1 over 3 cos x cubed plus k. Nice. All right, 8 marks for that. Now the second part says find the integral of e to the 2x over the square root of 1 minus e to the 4x dx. So to do this integral, again, I like to call it I. I just like to call my integrals I. So I is equal to, I'm going to rewrite this as the integral of, instead of saying that, I'm going to write I is e to the 2x over the square root of 1 minus e to the 2x being square rooted. Instead of saying e to the 4x, I write it as 1 minus e to the 2x all squared. That is e to the 4x dx. I still can't see what's going on yet. So what I do is I do another u substitution. U substitution is so powerful. So I do another u substitution, and I'm going to substitute u as e to the 2x. If I substitute u as e to the 2x, then my du is going to be, when I differentiate e to the 2x, when I differentiate this, I get 2 times e to the 2x dx. So looking at the question above, I need to put a 2 right here, and so I put a half on the outside. Now that I do that, now I can rewrite that I is equal to a half the integral of 2e to the 2x dx is now du, so it becomes integral of 1 over the square root of, this part now becomes u, so it's 1 minus u squared, 1 minus u squared du. And so I is equal to, now when you're integrating 1 over the square root of 1 minus u squared, that's just sine inverse. So I is now just a half sine inverse of u. So it's a half sine inverse of u plus some constant c. That's how we attempt this question. But we can't stop right here. Never stop right here. Remember I said u is e to the 2x. And so you have to go further. And then finally you can conclude that, of course, in this case what we're saying is I is equal to a half sine inverse of u, where u is e to the 2x plus some constant plus c. That is I. Nice and easy, soft. That's how we do this. Nice. Now right here is, it says use partial fraction to show that x to the 4 plus 1 over x times x squared plus 1 all squared is equal to 1 over x minus 2x over x squared plus 1 all squared. Use partial fraction to show that. All right, let's go ahead and do this. I'm going to call this I, because I don't want to write out back all of this. I'm calling all of this I. So I can be separated in partial fraction as a over x. I can be separated as a over x plus bx plus c over x squared plus 1 plus dx plus e dx plus e over x squared plus 1 all square. So this is I. All right. So now, of course, we're going to have to find the common LCM, primary school mathematics and prep school. So it's x times x squared plus 1 all square. And so we go x into this leaves x squared plus 1 all square. So it's going to work out to be a times x squared plus 1 all square plus this into this leaves x times x squared plus 1. So then it's going to be plus bx plus c times x. So it's bx plus c times x squared plus 1. And then we're going to go x squared plus 1 all square into this, just leaves x. Then it's going to be plus dx plus e times x. dx plus e times x. That's what we're going to get. All right, nice and easy, soft. So this is what we get now. Now, since this is what we get, all right, since this is what we get, now we can just proceed to go further and simplify this question. All right, so let's go. And we have to remember that this on the left-hand side, I is equal to this. So since I is equal to this, before we even simplify, remember I is all of this, we can just equate the numerators. So equating the numerators, that means that, let me put in, that's what we did right here, equating numerators. Equating the numerators, we are going to see that x to the 4 plus 1 is equal to all of this. So let me go ahead and work out what all of this is. X squared plus 1 all square is x to the 4 plus. So expanding this, I would get ax to the 4 plus 2ax squared plus a. That's what I get when I expand that side. Then when I expand right here now, I'm going to get bx squared plus cx. This is really bx squared plus cx, and then bx squared times x squared is bx to the 4, and then bx squared times 1 is just plus bx squared, and then I'm going to have cx times x squared is cx cubed, and then I have cx times 1 is just cx, And then I have dx times x is plus dx squared. And then I have e times x is just plus ex. Nice. It looks confusing, but it's very easy. What you're going to do now is you equate coefficients of each of them. So equating coefficient of x to the 4, we see that we have x to the 4 here, ax to the 4, bx to the 4. And so equating coefficients, equating x to the 4 terms. So this means equating x to the 4 terms. We can see that we're getting 1. The coefficient of x to the 4 is 1, is equal to a plus b. So 1 is equal to a plus b. Equating x cubed terms, there's no x cubed term here. So equating the x cubed terms, realize that 0 is equal to x cubed term over here is c. Cx cubed, so 0 is equal to c. And then equating x squared terms, there's no x squared term over there, and so 0 is equal to x squared term over here is 2a plus b. So 0 is equal to 2a plus b plus d. Then finally equating x terms, or penultimately equating x terms, we have cx plus ex, and there's no x term is 0, so 0 is equal to c plus e. And then finally equating our constants. The only constant we're getting is a, and so a must equal 1. This is equating constants. Now if a is equal to 1, and from equation 1 here, a plus b is 1, so that implies that b must be 0. b is equal to 0. And b is equal to 0. b is equal to 0. And we can see right here c is equal to 0. And since b is equal to 0 and c is equal to 0 right here, it implies that a is 1, and so 2 plus b, 2 plus b, so 2 plus d is 0, so d must be negative 2. d must be negative 2. And if c is 0, 0 plus 0 is 0, so e must be 0. e must be 0. So these are all the solutions. All right, nice. And so looking at it now, finally we can conclude now that that expression which we can call I is equal to a over x. A is 1, so it is 1 over x, plus bx plus c over x squared plus 1, but bx plus c is 0, so we can just forget that part, as we're really getting plus 0x plus 0 over x squared plus 1. But 0x plus 0 is just 0. All of this is just 0. All of this is 0. And then we have plus dx plus e. dx plus e, dx, that's just minus, because d, it have a minus, so it's minus 2x plus e, but e is 0 over x squared plus 1 all squared. So we're showing it. And remember that this is equal to this. So we're showing it. Oh, nice. So nice, man. Oh, nice. It's showing. Soft. Nice. Then it's a hence integrate this. Hence, integrating this means we're going to use what we just found out. So again, I'm going to call it I. Since I'm calling it I have now that I is equal to, instead of integrating this, we're integrating instead 1 over x minus 2x over x squared plus 1 all squared dx. This is what we're integrating. Now, we can always break them up into two separate integrals to say we're integrating 1 over x minus, I know I left off my dx, I know, minus the integral of 2x over x plus 1 all squared. Don't leave off your dx. I leaving off the dx, but you don't. So I just separate it now into the sum of two integrals, or the difference of two integrals. All right, and so now the integral of 1 over x, you get ln x. You can put mod x if you want, it don't matter. So ln x, some people like to put ln mod x, just depending. All right, ln x minus the integral of this now, minus the integral of this. Now I'm going to use u substitution here. So I'm going to let u be equal to x squared plus 1 or x squared plus 1. If I use a u substitution here, I realize that du would be 2x. And so I can use u substitution and integrate this. And so this becomes minus the integral of, in the numerator is du, and here is just u squared. So it's minus the integral of 1 over u squared du. And so what I'm getting is ln x, and it's ln mod x. Now to integrate u squared, it's going to become add 1 to the power, which is u to the minus 1, divided by the power of minus 1 plus c. Now what was u? Substitute back what was u. So this worked out to be ln the modulus of x, ln the modulus of x, minus and minus give you plus, so ln mod x plus, u to the minus 1 is really 1 over u, so that's going to be plus 1 over u, u is x squared plus 1, plus c. Nice and easy, soft. So that's how we do this question. Nice.